we're still going to carry on in shearing stress for thin wall. So yesterday, right, what we have done yesterday is we formed the equation of the distribution of the shear stress. Okay, so we form two functions. Okay, so we have this diagram over here, which I'm going to bring across. Okay, right. So you can see over here, we need two functions which we have developed. So so the first function is when the thickness, just to quickly recall, is 0.16 meters, and the limits range from 0.015 y, and it goes up to 0.035. Okay, so we have derived the formula, and this is the first function that has that limits. Okay, so copy. Right, so we have derived this, and the next one that we have derived, okay, is when the thickness is equal to 0 or twice of 0.02, which is equal to 0.04 meters. So this corresponds to 0, the limits of 0 to y, and go up to 0.015 meters. Okay, so we have derived another function, and this is the one. Okay. So I'm going to copy. Then we're going to paste over here. Okay, sorry. I think I copied the wrong function. It looks exactly the same, which is wrong. Okay, I think the first one is 0.0741. I think I have to go way back. So the other one is 3.327. Sorry, is this one over here? Okay, 3.2707. That's the one that has the limits between 0 to 0.015. I do apologize. I copied the wrong function. It cannot be the same. There you go. Okay. And then we also found out that this function over here, okay, is also valid from minus 0.065 y and go up to 0 meters. So this function, right, knowing that when y is equal to 0, which is at the centroid, and we know that this y is positive going down, y is what? Y is negative. Okay. So we are aware that when the y is negative from 0.065 to 0, the function is still valid, right? Remember, we derived over here, right? Yesterday, we derived by focusing on the bottom of the structure. Remember that? Okay. So we realize that the first moment of area we get by just considering the bottom, and the first moment of area is exactly the same. No doubt if you see how the top one has been developed or derived, and how the bottom one has been derived are not the same numbers, but the outcome, the function, is the same. Okay. So where we are now today, what we are going to carry on, if we look at the problem, we are going to look at the resistance force. Okay, the resistance force for the flange and the web. Okay, so next we are going to calculate the resistance force of the flange and web. Okay, and I'm going to address this as our equation number 1. Okay, and this as our equation number 2. Okay, so we are going to first find out what is going on with the flange first. Let me get this diagram so you can see what we are trying to deal with. Okay, so we're going, so resistance force means how much force is taken up by the flange, okay? How much force is being carried by the web, okay? So we are going to consider the flange first. And the general equation to use is force is equal to, we're going to integrate shear xy, or the shear stress, as a function of y and dA. Okay. So by looking at the flange, we know the limits is what? By looking at the flange, we know the flange limit relative to the datum is 0.015 y, and it goes up to 0.035. Okay. So we know our limits. Okay. So the force, resistance force of the flange will be equal to the limits of 0.015, the bottom limit, the upper limit. Okay. The shear stress, we have to use equation number 1. Okay, because equation number 1 is operating at those limits. So you get 9.483 times 10 power 6. And then we have minus 7.741 times 10 to the power 9 y squared, right? And then you have dA, right? So the width is constant, right? So we know that the width is constant, 0.16, and the y is changing, dy, right? So now the thing that we are going to do now, we are going to do a very simple integration, right? So this will be equal to 9.483 times 10 to the power 6 y minus by 7.741 times 10 to the power 9 y cubed, and then we divide by 3, and then we go integrate within the limits of 0.015 to 0.035, and then we multiply by 0.16. I'm going to move the 0.16 into the brackets. So you will have 9.483 power 6 times 0.16 is equal to 1.517 and then minus 10.741 pound 9 divided by 3 times 0.16, 412.853 times 10 to the power 6, and you have y cubed, and then you have 0.035 and 0.015. So with this, when you substitute the values in, okay, you will have 35.394 times 10 to the power 3. Let me do it. 0.517 power 6 times by 0.035, and then minus by 412.853 power 6 times by 0.035 power 3 is equal to 35.394. That's correct. And then we minus, okay, 1.517 power 6 times by 0.015 minus 412.853 power 6 times by 0.015 power 3 is equal to 21.362. 21.362, yep. Times 10 to the power 3. So it's good. 35.394 power 3 minus 21.362 power 3. So it's equal to 14.032 times 10 to the power 3 Newton. Okay. So this is the this is what we call the resistance force by the flange, which is equal to 14.032 times 10 to the power 3 Newton. Now we can also, with this value, you can also immediately calculate the resistance force of the web without doing the integration. Okay, so how do you do this? So total resistance force carried by the structure, which is equal to your Vmax, and this is equal to 90 times 10 to the power 3 Newton. So the 90 times 10 to the power 3 Newton is taken from here, right? By looking at this diagram over here, right? Our shear force diagram is positive 90, negative 90 does not matter, because whether is it positive shear, negative shear, both are as bad. Okay, there's no such thing that positive shear is better than negative shear. Okay. So with this, we can immediately calculate the resistance force. Okay, resistance force by the flange, sorry, by the web, which is equal to 90 times 10 to the power 3 minus by 14.032 times 10 to the power 3. Okay, so 90 to the power 3 minus by 14.032 to the power 3 is equal to 75.968 times 10 to the power 3 Newton. Okay, so that is the shear force, resistance shear force taken by the web. Okay, so to see is this true, right? To see is this true, I'm just going to do it in as an exercise. We are now going to find using force